So in section 4.5, we're going to be looking to find solutions of our quadratic equations, and that's going to look like x squared, x, and a constant, kind of like we've seen before with factoring. In a graph, we'd see this kind of quadratic equation is what we call a parabola shape, and if I was looking to find the solutions, that would be the zeros or the x-intercepts of that graph. Here we're going to solve that instead by factoring, and when we factor, we're going to be looking to get our equation to look something like this, where I have two values that multiply together to get 0, and that means if I can solve either one or the second value, either finding where the first or the second is 0, that's going to imply our solutions. So to use that zero product property to solve a quadratic equation, it's not going to work unless that equation is set equal to 0. So it looks like in this first example, I do want to take a step before I begin factoring, and that's to add, it looks like negative 12 to both sides, or I guess add 12 to both sides, get that to cancel. So if I add 12 and I have that right-hand side that's equal to 0, now I can apply my property as long as I can factor this in a way that I just have two binomials instead of this trinomial that we begin with. If I just have x squared and no leading coefficient before that x squared term, it means that I'm looking to fit my pattern. I need two numbers that multiply to give me 12 and add to give me negative 7. If I think of my multiples of 12, this is also a case I want to consider that both of those factors should be negative, because again, two negatives will multiply to give me a positive, and they're also going to add together to get me that negative sign. So we're going to be seeing that already for my answers. If we want to structure what that factorization is going to look like, we know that our answers are both going to be x minus and x minus, just because again with those factor choices, both of those do have to be a negative value. It looks like from those options, negative 3 and negative 4 fits my pattern, multiplies to give me 12, and it adds to give me a negative 7. So if I can factor my expression that way, previously it'd be done, but now only step if I'm looking to solve this quadratic equation, since that is again equal to 0, and we factored this left-hand side to get those two binomials, now I know by using my zero product property, I can set either one of those two expressions equal to 0. So x minus 3 can be 0, or x minus 4 can be 0. Either one, again, if they were 0, multiplying by 0 is going to give me 0 for that entire equation. So pretty fast to solve if I have those separated. If I just add 3 to both sides, I just get x is 3. Add 4 to both sides, I get that x is 4. So these would imply that both of these are possible solutions. X could be 3 or it could be 4. And if I substitute those back into my original equation, I would get an equation that's true. Because again, I would be able to get a 0 if I add that 12 to both sides. I'm going to look at our answer underneath here before we look at part B. Again, part B with that leading coefficient means that we would have to take another approach on that question. But looking at your answer, if you guys want to try that one down below for part A, x squared minus 5x plus 6 equals 0. First step is pretty much the same as what we've seen from before with our factoring. We do want to make sure we can fit that pattern, multiply to get 6, add to get negative 5. As we saw in that previous question, that would require two negatives, so negative 2 and negative 3 looks like they fit that pattern. And as long as I'm able to factor that out, that was most of our work. The only step that we're really adding that's new is the fact that if either of those binomials can be 0, I just want to solve for where I get a solution on each one. Adding 2 to both sides, I get x equals 2. Adding 3 to both sides, I get x equals 3. That's two possible solutions to my question. So going back up to our second example where I have that leading coefficient, again, as soon as I see this 5x squared, I know I can't just take that same approach with x method that we used on that previous question. Again, that would only apply if I have that x squared term. This is our approach that we're going to have to take by breaking down the factors of our first and our last term. So 1 and 5, only way I can multiply to get 5. And again, if I'm trying to break down the factors of 32, I want to break them down in a way, just like with this method that we practiced before, they're going to multiply together, cross multiply rather, and get 28 as a result. So if I think of the factors of 32, I think if I use 4 and 8, and if I use them in that order, again, we're thinking of this in terms of cross multiplying, 1 times 8 and 5 times 4. 5 times 4 gives me 20, and 1 times 8 gives me 8. So if I do add those and I get 28, it looks like that's going to fit my pattern, and that means that the factorization of this left-hand side, again, knowing that the right-hand side is still going to be a 0, means I could factor out each row, x and 4, so that's just like a 1x and a 4, 5x and then 8 if I was factoring out that second pair. And you could always double check by foiling box method that one and see that you get that original trinomial. But it does look like that's my correct factorization. And just as we've seen on that last question, I could apply my zero product property at this point. So I know that either one of those two binomials could be 0. That's going to be a solution to the entire equation. First one's pretty easy to solve. I can just subtract 4 from both sides. And second one is also pretty easy, but just take one extra step. Subtract 8 from both sides, divide by 5. And that does give us two possible solutions for x. So at this point, you could just say either one are solutions, or pretty commonly, you're just going to see them both listed, negative negative 4 and negative 8 over 5 both being solutions. But as long as we know that those are both options, those would both make my equation true, that's going to be two solutions to that quadratic equation. Trying that with the question down beneath, and kind of for the same reason as what we saw in the last question, there's no greatest common factor. I can't divide 2 from every term here because we have an odd in the middle. We're just going to be left with like that 2x squared, so I can't just take my x approach as we did on part A. Trying that question again by matching with our terms, 1 and 2 is the only way I can multiply to get 2. And if I'm trying to choose this in a way that's going to add to get negative 19, my cross multiplication here, factors of 24, it should be negative 8 and negative 3. Again, multiply to get 24, and when I cross multiply 2 times negative 8, I get negative 16. 1 times negative 3, I get negative 3. Add those together, it does give me my correct middle term. So it looks like those were our correct factors. As we did in our last question, we want to combine those rows together. 1 and negative 8 means that that's how I'm going to factor my first binomial, 1x minus 8. And then with our second row, 2x minus 3, that's our second binomial. Again, if you wanted to double check, you could FOIL this and get back to your original trinomial if you wanted to reverse that process. But since this is the correct factorization, I'm just looking to use that zero product property and knowing that each of those binomials could be set equal to 0, and that's going to come up with a solution. So if x minus 8 is 0, that implies that 8 is a solution. And if I set 2x minus 3 to be equal to 0, again, just one extra step there, add 3 and then divide by 2, that gives us our second possibility for that question. Also a good idea, again, if we had the time, if we had a calculator, take this answer and plug it back into your original trinomial, plugging in 8, plugging in 3 over 2, either one, if I substitute that in for x, that would give me a solution to the original equation.